Okay, I see some people coming in. There's Sadhu. I recognize Cole's name. Steve's name. Great. Chris, I see you. All right, here comes some more people. Really, now the gates are open. Okay, good morning, everyone. We've made it to the middle of April. It is April 17th, and we are back with Duane for another installment of the Codes Updates webinars. Today's service water heating, and he's brought Shawn back. He was, I think, it was the service water heating one last year, 2023, actually, maybe it was. Um, and they're going to give us all of their knowledge today on this topic. And I am Katie with the Lighting Design Lab, desperately trying to find my notes page. There we go. And we are going to start off with a Slido poll. It's nothing tricky, very easy. Probably the easiest thing is get out your phone and scan the QR code. It'll open up the Slido page quickly for you. If you'd rather just type it into a browser, open up another window, go to slido.com. There's two different codes you have to put in. It's locked down tight at Slido. 2299529 gets you into today's poll, and that 0YQYBM will get you into the questions. And this information is going to be on the next couple of slides, so don't panic when I click next slide. If you have not had a webinar with us before at the lab, this is kind of the rundown of how it goes. You are all on mute the entire time just for flow, not because we don't value your opinions. Send all questions, comments, constructive feedback in the questions box thing. Look for the questions icon on your toolbar. It might be at the bottom of your browser window. Click that. You can submit a question at any time. I will be back in the background keeping track of them for the end of the session, unless it's really pertinent. We really need to interrupt. I enjoy interrupting. Let me do that. But we'll try to keep the flow going. The webinar is being recorded, so if you have to step away or at the end, you're going to find this so valuable, you're going to want to send it to your friends. So it'll be available on our website within about a week. Give me about a week, and I'll put the recording up along with the slides, so then you can forward it to your friends and family, enemies. And there's a survey at the end. Please take that. It's really valuable for us to in programming, our speakers. If you want to hear about a topic more in depth, we need to know that. So let us know. The Lighting Design Lab has been around for a long, long time. We're in the middle of being rebranded because we've expanded our services to technologies beyond lighting. Actually, we have a meeting next week. We're going to see some tentative proposals about what we might transition our name to. So that's very exciting. And here comes the actual Slido
This is the
poll.
fourth year of the rebranding effort, right? We're almost there.
Man, you know, I guess I'll be a gracious host and say, yes, Duane, you're right. Okay. Anyway, we would like to know what your job title is. Where are you at today that we're talking to you? So design engineer, project engineer. Um, People are typing. Building performance and good. Okay, thank you. Yes. Yep. Perfect. Plumbing designer. Nice. We want to know what you want to know. Okay, good. I'm going to go to the next slide real quick. And then, where do you do your work? Are you local-ish? Uh, outside the states. We once in a while will get, other states, and even Canada logs in and wants to know what Duane is doing here in Seattle. All right. Thank you everyone for participating. And that is all I have for that Slido poll. Just really quick, I'll let you know about our upcoming events. We're going to have Levin Knock from Design Lights Consortium come talk about integrating lighting controls to help with some HVAC savings. So we'll hear what he has to say about that. Duane's going to be back for the last of our series this year and talk about alterations, stuff in the code. And then open soon, we're going to have City Light is releasing a distributed interconnection handbook in July, I think. And in June, we're going to have a whole webinar on how to use it. It's going to be targeted mostly at solar installers, but it'll be good information to know for anybody that's considering mostly solar, but it's interconnecting to our network. And then we're going to have Mike Fowler from Methune come talk about passive design. So that should be a really cool topic. He's got a couple of conferences he's going to be at. If you missed those, come watch this. And with that, Duane, are you ready? You're on mute. I'll give you a second. I'll vamp a little bit.
No, you're
And
good.
okay, good.
But can I just start sharing on top of you, or
Yeah,
you need to share first? All right.
I don't need to. All right. Thank you, Duane and Shawn. Take it away. I'm going to go around and everybody submit your questions, and I'll round them up for the end.
All right. That sharing does not seem to have functioned, so let's try again. Are we sharing?
We got the slide, like, the software, not the presentation mode.
Sweet.
Do you have it started in presentation mode in a different window?
Are we there?
Nope.
This all worked 10 minutes ago when we did our rehearsal, but we will undo that.
Yep, and you've got it started in presentation mode somewhere, right?
Just
Prior. Okay.
make sure that we're good to go there.
Yep.
Yes, we're in presentation mode. Um, I can't believe this is happening again.
Right. So
Let's
unshare.
all right, stop sharing. We're gonna get to this and out of that. We're gonna um, this is peculiar. Okay. Just talk amongst yourselves.
Yep, yep. I was gonna say while you're figuring out your presentation,
Terrible.
just so everybody knows, because a lot of people have logged on since I started talking, this is being recorded. We might clip this part out. This is being recorded and will be published on our website within about a week, lightingdesignlab.com. I'll put that in the chat part of the functions. Even though you can't use it, you can read it. And if you have any questions at any time, go to the questions icon and type in that function, and they'll come to us, and we'll get those answered by the end of the webinar. And one thing I skipped over just to keep my intro short. Seattle City Light has a trade ally network now. I'm going to turn my camera back on. It feels weird to look over and see Shawn and Duane and not have my voice. Um, Trade ally network. So architects, installers, contractors. Um, it's just starting up now, but we do have blocks of time dedicated that you get 15 minutes uninterrupted time with the people that do the incentive programs. They can give you tips and tricks. They can, confirm that something that you've got in mind will qualify for incentives, or if it doesn't, potentially figure out with you what might. That's the third Thursday every month. The next one is tomorrow. I don't remember when they close the um, registration, but um, I'll put the link in the chat for that, and we'll let Duane go now. Ready?
Ready. Okay. So who all is tired of seeing this screen? But we have at the state and the city level some very ambitious goals in legislation, which is unlike how other jurisdictions work. And we have these four guiding principles we've been using for a few code cycles now to develop new ideas for the code, and a couple of them are circled there for today's talk. We're happy to have Shawn along again, and he's somebody I go to over and over again when I don't understand something. He patiently explains again and again how it works. Welcome, Shawn, and take it away.
All right, thanks, Duane. Good morning, everyone. So we've done a couple of these presentations, but I'll just run everyone quickly through kind of big picture and some basic concepts. But so right now we're looking at kind of the multifamily energy end use. That's the graph over to the left there. And that shows kind of our existing case. And we can see the red and that orange, those represent the hot water load and the hot water circulation or the temperature maintenance load in that orange area. And by using a heat pump, we can reduce that energy quite significantly. So the pie on the right kind of shows the after, and that green represents the savings. So it's a huge savings. It's one of the biggest measures in multifamily, and that's sort of what the focus is today.
Not only multifamily, but hotel, restaurant, hospital, any place that uses a lot of hot water.
Thank you.
These are our basic targets, that we're trying to establish. We're trying to get rid of that red triangle on the left there over the next couple of decades, and we can increase our clean energy a little bit, but most of that is going to be done by going to higher efficiency equipment. It looks like this is possible, and that on the right is where we're supposed to be going at the state level, and as you can see, we are pretty much on target. But those last few cycles that we're going into are going to be tough. We got to reduce another 40% or so to hit the state mandated target. Heat pump water heating used to be a requirement in the Seattle code. Now it's in the Washington State code as well. And to respond to legal challenges coming out of a California court, we also have a fossil fuel compliance path that lets you use gas if you make your building just as efficient as one that was a heat pump building. There are, you can see there's this requirement, but then there's this whole list of exceptions in there. A very popular one is that top one, but the one I have in red, the NEA advanced water heating specs are pretty interesting. They have a lot of systems, and those are we're now on version 8, but they've added this commercial multifamily module a few years back with 4 tiers of, and you can meet any of those tiers to qualify. We're saying this is just as good as our exception. They have a qualified products list that used just last year. That was, there were a half dozen systems available, and now it goes on and on. Lots and lots of manufacturers have had their systems certified through this NEA page.
All right, we'll jump into some of the basic components. This is kind of a review from what we presented previous times, but there's really 4 basic components of a heat pump water heating system. There's the actual heat pumps doing the work of heating the water. There's the primary storage tanks. We've got temperature maintenance systems. That's keeping the lines and the hot throughout a big building. And then we've got the mixing valve. Those are kind of the 4 basic components, super important in any heat pump water heating system. And then we talked about kind of the heat pump water heater or the engine. This is providing all of the heat for the hot water heating. There's an array of products out there. We'll dive into a little bit of that, but the market is developing. There's 7, 8 major players here in the Pacific Northwest. The reps are kind of the key to the market and the distribution and the design support, and that's been quite intentional the way that's been laid out. Next. Oh, so this one is just making the argument that the heat pump water heater is really the engine, or the device replacing the boiler. Boilers are typically much larger than heat pump water heaters. These systems work with heat pumps taking care of a larger storage volume. So it's sort of the little engine that could, and that's how we have to think about these in our big buildings and small ones.
And Shawn's an actual engineer. I call myself a PE, but it means pretend engineer. And for me to figure out how this works, it's basically just this miraculous fluid that they run around that they call a refrigerant. And basically on the left, you got cold air that's coming out, and if you stood in front of one of these, even colder air goes out the other side, because heat is being pulled out of that and put into this compressor, squeezes it, and so it's a really hot gas, and then that heat is transferred to the hot water on the right, and by the time it's done transferring, it's down to being a liquid again. It goes out and gets even colder, and this just cycles around as long as your heat pump is running. It is really slick, and it uses a third of the energy of trying to just generate your heat from burning something or running electric resistance.
And this is kind of another way to look at it. Depending on your understanding of the pressure enthalpy curve, it's a nice way to look at it. But it's essentially kind of the physics behind how that cycle that Duane just looked at works. But it's essentially, there's 2 coils on the indoor coil. In this case, it's a hot water tank. The outdoor evaporator coil is outdoors, and that's where the heat comes from. So this is really important when you're setting these up, is you got to make sure you've got a good source of heat for the outside coil. And so one thing that's really important, as there's 2 ways to kind of heat the water up. And when I say two ways, I mean the manufacturer's heat pumps are set up to either provide single pass heating or multi-pass. Single pass is where we take really cold water and we lift it to the final working temperature in one pass through the heat pump. So these tend to be really slow, much slower pumping rates and larger storage, and you're just trying to kind of stay ahead of the next cycle, peak cycle load inside of a building. The single pass stuff is tends to be kind of refrigerant dependent, and the multi pass stuff on the other side. This is a very similar analogy to kind of gas boilers, but you're essentially just heating up, 10-degree delta, 15 across, and heating up that hot water tank till you get to the end. I think that's all there is there. We talked about kind of the different pieces inside of a heat pump water heating plant. The storage tanks are kind of the primary engine. There's a lot of BTUs and a lot of water that's kind of stored up. So the idea is you're making this water offline with a heat pump. You're storing and buffering up a large volume, and then the building is sort of pulling off of that large storage volume. So we kind of call this the battery bank. And this is actually quite a resource for buildings, is having this large storage. You can start to do things with managing when your heat pumps run. And that's sort of another piece coming in the future, which would be about demand response or load shift.
And you could also do this by just buying a whole long row of heat pumps, but it would be way more expensive than just buying these tanks and letting them heat up in the off hours.
Yep. Correct. And we talked about kind of the third component, which is temperature maintenance systems. But really, it just summarizes as keeping the water in the distribution system hot. That's the point there. With big apartment buildings, you have to keep these circulation pumps running pretty much all the time. And as a designer, you sort of want to tackle both you want to really look at the COP of those the temperature maintenance load, because it is significant. It's 1/3 to 1/2 of the total hot water load. And so in bigger buildings, you might look at treating that temperature maintenance load with a dedicated heat pump. In smaller buildings, you can get away with a swing tank concept. Next. So we mentioned the single pass and the kind of the multi-pass. We mentioned, and this one is really focused on the temperature maintenance, which I just mentioned, but you can either set up a system as a swing tank type system. So you've got a primary storage feeding what we call a swing tank. The swing tank name comes from that temperature in that tank is swinging, up and down. It's not a steady temperature. And so it does vary, but the idea is you've got hotter temperature in that primary storage, and that will sort of mix with the cooler return temps. And so what comes out is sort of temperature that's usable, that goes, that advances to that mixing valve. And then when we get into bigger buildings, or we've got existing buildings with bigger loads, at some point it makes sense to kind of look at a dedicated heat pump for that circulation load or that temperature maintenance load. But that's generally where that gets applied. And it also is somewhat dependent on what the load profile looks like, because you get a lot of buildings, if they're not drawing water overnight, you're either turning the circ system off or you're keeping it charged in case it does need to stay on.
So which kind of buildings would use the swing tank versus the having that maintenance heat pump?
Yeah, that's a good question. I would say that the swing tank works really well when your primary heat pump can heat up to about 140, 145. There's some heat pumps out there that struggle to get to that temp when it gets cold out. And so I usually kind of match a swing tank up with the type of heat pump. And I would say that those tend to be kind of smaller systems. They can be done with bigger systems if you've got a really big load, but those tend to be 100-unit apartment or less. That said, we've done them on larger buildings too. And so I would say it's kind of smaller stuff with really good distribution systems, because the swing tanks really shine when you've got really well insulated distribution systems. So
And
that
what,
would be kind of new construction where you've really got a chance, or if you're doing retrofit where you can really do a good job with the temperature maintenance. And then on the where you've got a parallel loop tank, so you've got a parallel, you're still doing kind of single pass, but a parallel multi-pass on the recirculation, which is that diagram to the right. Those are, I think, better for when you've got really big buildings with really big kind of circulation losses, or you've got older buildings that have uninsulated or poorly insulated hot water lines.
we'll get into pipe insulation in a while.
And this is that fourth component, which is a thermostatic mixing valve. What we've found in our sort of field work is that you really have to use these motorized mixing valves because, and the reason is the temperature maintenance tanks, which become the hot supply on these systems, they vary a lot depending on kind of the heat pump design and how it's set up. And so when you've got variation in the hot side, that can really screw up a mix if you don't have something that's dynamic and can feed back and adjust. The other part that's really important is making sure you're sizing that thermostatic mixing valve properly. We do a lot of commissioning of other projects, and oversized mixing valves is definitely top 5 issues that we've seen and had to address. But they have kind of a sweet spot in the range, and you size those based on the recirc load plus your kind of peak and your peak loads, and then you need to make sure that those are selected properly.
So a couple things on the circulation control. It depends on whether you're a single riser or a multi-riser system. With a single riser, this is a very simple system. Then it's just saying it's gonna heat up until to the target temperature, and then the pump will just turn off until that return side is 10 degrees below that supply temperature. Or you can have an automatic time switch that just turns it off. This works for buildings that have unoccupied hours. Note that if you're residential or institutional, then there aren't any unoccupied hours, and you don't need to have that control. With multiple riser systems, Shawn will get into this to some extent, but if there's an extended period like a holiday, then the pump would go off. But there's some means to balance the flow rate. Seattle requires a thermostatic balancing valve for that, so that different loops in the system can be running at different rates.
One thing maybe backing up there, Duane, is that the Group R is exempt, and
Right.
I've seen some other projects where we've tried to turn the circ pumps off on Group R, and I don't recommend it. And so that's really an important exception there.
Some people need to take a shower at 2 a.m, and
Yes.
so Group R and Group I, so that would be hospitals and nursing homes and correctional and like that.
Thanks. So some of the kind of key design considerations, we'll kind of touch on these 4, but the building hot water distribution systems and kind of looking at the impact of thermal stratifications in your plant will be one. We'll just brush briefly on some of the tools that are out there, have been developed. EcoSizer has been around for 4+ years, and it continues to evolve with additional California funding. Refrigerant and equipment selection. So this is a pretty hot topic now. Refrigerant phase out is sort of happening, across HVAC and hot water. And then the importance of alarms and notifications and kind of proper training with your maintenance. Those are kind of your key pieces as you're diving into designing with these systems. This is an example of a project in Pasadena, just to kind of show down in California. But this is a CO2 product that's out there. It's been in the market for about 15 years now. We've had a lot of success with this. Just kind of shows you, an example of an installation. This thing's been running for about 2 years. It's been purring away. It's working great. This is 77 units senior housing. This was a kind of a rescue design because this was one of the early heat pump water heating designs that didn't work quite well. So we came in and helped out.
And what we're looking at is 6 heat pumps and 3 big tanks. Is that right?
Yep, for 77 units.
Yep.
So this is really, it's heavy on the storage on that particular design.
Right.
But yeah, just kind of this reiterates the point. It's sort of the little engine that could, and that's how we want to think about these systems. And then we kind of look at the upper end of the scale. So this is a project that's been in service probably 5 years or so now. But it's 525 units. It was served with 2 plants. They look similar to this. These heat pumps are located in a below grade parking garage, which is a great thermal resource. And this one, and this one's kind of been operational for 5 years, like I mentioned. But these systems can be designed for projects big and small, so just kind of shows the range. Another exciting area we touched on this last time are kind of fully configured skids. As we start to kind of decarbonize buildings, solutions like skids are I think nice plugins for existing buildings that don't have a lot of extra space. They also are really nice because you can keep the occupants' hot water supply up. This particular project shows a skid built system using a Mitsubishi, and this is serving 100 unit apartments. And this switchover was done in 4 hours. So the tenants, we did this overnight. But this is the importance of having the skidded out equipment, is because you can just do these swaps overnight, a little bit of planning up front. But this is an exciting project. We've been metering lots of experiments looking at load shift with this one. So a lot of stuff on this.
For permitting on heat pump water heaters on the commercial side, where what you see in the red box in the middle is the King County Public Health Plumbing Division. They're looking at all the water connections, the potable water connections, and the pipe installation. They're the condensate. They're concerned with those plumbing and public health related things. On the left, you see our mechanical people deal with the actual water heater itself and any kind of fans that are required to get air into it, and anything that's architectural or structural or noise related would go through a mechanical permit. And then on the right, you see Seattle has a separate boiler division, so we require that any of those big storage tanks with hot water gets separately permitted and will get inspected annually to make sure everything is ship-shape. They're mostly concerned with the safety aspects of it. For sizing, Seattle requires that you size the heat pump to handle 100% of the expected load when it's 40 degrees out, and 50% when it's our design low temperature of 24. In Washington State, it's half that, although we have a proposal up for next code to see if the rest of the state will go with the 100%. Because who wants to design and build and pay for 2 separate systems in the same building? But you can tell that was a political thing. And Ecosizer, well, why don't you go ahead and talk about it?
Sure. So Ecosizer was developed about 10 years ago, and this was using kind of the latest curves in ASHRAE, which required you to set up like an iterative calculation to figure this out. And so this tool is developed to kind of help designers through, and we haven't, we've done a lot of designs with this tool and have yet to sort of run out of water. So that's my testimonial on this. But it's just straight math on the BTUs used, when it's used, and do you have enough storage to keep up? But there's a
And
lot of cool feature in it too.
in case it's not obvious, that there's kind of a slider in there that I've played around with. It's kind of cool that you can make your storage bigger and your heat pump capacity smaller, or vice versa, and you can sort of slide back and forth along that line to determine what's kind of the most economical combination for your project.
Yep. And one thing I would say, just backing up there for designers, typically the way that we use that curve is we'll establish our kind of capacity at design. So, pick your design temp, 24, 23, 19, what you want. And then you look at the output of your heat pumps plant, and then you start there with the capacity, and then you move that bar until you match that capacity. And then what's left is your storage. You want to make sure you got at least that amount of usable storage.
So that gets you through your morning rush when everybody's taking showers in the building.
Correct.
So one thing I just wanted to point out regarding the sizing of pipes in your system, that row of black dots on the bottom is a couple dozen apartment buildings that were measured in real life to find their peak hour usage. That represents the actual peak hour usage. The row of dots on the top is the system we've been using since our grandparents' generation to size those pipes. You can see it's 15 or 18 times the actual flow. So we're going to be talking about Appendix M, but we're requiring that you use Appendix M, and that overstates the peak load for almost all those buildings by a factor of 4. So you're really in safe territory, and those great big pipes that have been requiring a huge amount of circulation pump energy and heat loss from those big pipes has been really wasteful for all these generations.
Yeah. All right. So I guess we'll kind of dive into temperature maintenance, kind of the distribution side. There's a lot of ways to distribute hot water in buildings. Rib cage is kind of a common term. This kind of shows how that works, but you essentially get up to level 1 of a multi-story, multifamily building, and then you spider out into risers on that first floor, and then run up the stacks. And then you grab those stacks at the top and bring them back down. You can bring them back down in a single return. You can bring them back down in multiple returns. ASPE has calculations to kind of estimate what your heat loss rates are, and that will determine how far or how long of a distribution system you want. Because you do have to keep in mind that as this distribution system grows out at the end of the line, you're going to drop temperature, and you got to be sure you don't drop too much. Next.
So we mentioned single pass versus multi-pass a number of slides back. With that single pass system that boosts your temperature from 50 degrees incoming water to 140 or something like that, all in one swoop, the temperature maintenance heating has to be physically separate from those tanks. And as Shawn mentioned, you might be able to accomplish this by just having warmish water that's in that tank that then gets combined with the hotter water from the storage system. But somehow it's got to be separate. If it's that multi-pass that Shawn showed us, then that recirculated water coming back from the loop can go back into the primary system, because that's what it was built for, was just increasing that temperature at 10 degrees each swoop. And finally, there are unitary systems like the one I've got, in my house here now, that is just sized to meet that load internally, you can do that if your indoor air supply is coming from a heat pump or some waste heat system, uh, because you don't want to be heating up the interior air with electric resistance or gas, and then using that heat to heat your water. You want to, if you're going to be heating your water with interior space air, then you want to do it. You want to have that air heated efficiently to start with. There's different. Some people in Seattle are still using in-unit water heaters, like you see on my list on the right, which would mean that you got 102 units, you got 102 water heaters. Developers had problems with, if you got 100 water heaters, what are the chances during this next year that one of them is going to fail and start leaking rusty water down into the apartment below? They don't work well in small spaces because they can actually get it below the dew point and start condensing water on your walls in there, and you could have cool water spilling out through the rest of the apartment. So not a real, in my opinion, not a real good idea, but some developers like it because it's all in one place. A central location, if you're using a CO2 based system, like Shawn's mentioned a couple already, then you can have them outdoors. You can have them in the garage, you can have them in the roof, garden, and we already require a separate water meter for each apartment unit for hot water delivery. So the owner can still bill tenants for their hot water use.
Yeah, and then back on the hot water distribution stuff. So the thermal stratification is sort of everything in hot water storage. You can set up, these systems in parallel. You can set up your tanks in parallel or in series, but the stratification is super big. And the point that this slide is trying to make is that when you do a return to primary, so your hot water circulation loop is coming into your primary hot water storage. If your heat pump goes out, that hot water circ system will drain all of your water out in about 15 minutes. 15 to 20 minutes, and I've had this happen to me. So the reason to keep them separate is that you can preserve that really hot buffer of storage, and if the heat pump goes down, you've still got a day or two to kind of save you, or half a day. And that's sort of a reason to do that, to kind of decouple them, because everything's happening pretty fast, and so you don't want to, you want to be careful that if the heat pump goes out and your hot water circ comes in, it'll wipe out all your storage. But that's really, I think, from a distribution standpoint, that's the reason to kind of keep that temperature maintenance system isolated from your kind of, your gold, your hot water that's primed and ready to go.
And would you also recommend that rather than one giant heat pump water heater, they have a couple of medium-sized ones?
No, absolutely. And I think that, this reliability and, kind of the reliability and redundancy plan on your heat pump, I would recommend that, you at least do 2 heat pumps at a minimum. So just instead of, 1 10-ton, you do 2 5s as an example. It just gives you, a chance that one of them is still operational. And you can meet quite a bit of load with just the one. But definitely have to take your kind of reliability into account. When heat pumps get cold, they start to defrost. That's a whole nother piece, but that's a reason to kind of have multiple, is you can allow some stages to be running while other ones are defrosting. So this is kind of making that same point that I mentioned before, but with the single pass and the dedicated systems, you got a system for temperature maintenance and a system for the hot water load. You get better kind of equipment reliability. You get more, higher effective storage volume, better COPs, because each of the heat pumps are sort of designed for their function. So the one in the single pass with the dedicated, that heat pump would be a multi-pass, and then the one on the left, on that left diagram, would be like a single pass. But that's the reason to do it, is in case stuff kind of goes south in one of those heat pumps, you've still got, the storage. And then the multi-pass, these are going to be cheaper ways to kind of heat. They're very synonymous with gas boilers, kind of how we've been doing those. Return everything to one big tank and out you go. And I've seen these systems work. We've got a couple in our design, but with the recirc running through there all the time, your heat pump, your primary heat pump, is going to be running pretty much 24/7, just because there's always flow going through it. And then that can impact your performance too. So just hammering this down once again, but the temperature maintenance, you either have a swing tank approach. Again, that keeps it kind of separate from your hot water storage, and that's the system on the right, or you've got a parallel loop tank. And so that's just a multi-pass heat pump dedicated to maintaining that temperature maintenance tank. But those are kind of your two options to kind of preserve large storage volumes on that primary storage. Oh, and then we've got some points to be made here. Okay, yes, here we go. So on the sizing, this slide is just trying to kind of show that the sizing is sort of everything. We've got two similar sized buildings. The one on the left, this was actually the system in Pasadena that was oversized with a 410A heat pump, and it wasn't working. There was a lot of problems with it. And so we ended up replacing it with the Senko 2 on the right. But this project on the right is a project in Capitol Hill in Seattle, and it's a 60-unit senior housing project, and it uses 4 Senko 2s. That's 5 tons to handle 60 units. That's a little on the underside. This is one of the first ones we did, but this thing is still cranking away. It runs about 22 hours a day. It's not ideal. We'd like to run these systems closer to 16 hours a day.
And that's the one that's sitting out in the garden next to this unit?
Yeah. I mean, this is just a ground floor of a 3-story, 60-unit apartment, senior housing apartment. And that's just sitting outside of a mechanical room, but it's just outside, and we just did a retrofit into the existing hot water storage.
And I've seen that, and one thing I noticed was that it doesn't make any noise at all. And I mean, it's really, you just hear kind of the whoosh of the fan, and it's, they got plantings in front of it, so it's not really all that apparent.
Yeah. Yeah, those are nice machines.
Yeah. And they have a famous photograph, I think, of one of these got clobbered by a falling branch after a snowstorm, but the rest of the system was still just running fine. It didn't skip a beat.
Yep. Yeah.
Go ahead.
Yes, I think that's all to kind of talk about there.
So we can have supplemental heat, different from that primary water heating, for temperature maintenance, like we've talked about, for defrost if it's necessary on your system. You can have heat trace on a pipe if it's running through a cold area. You can use the supplementary heat if you're following all these rules that you're not using it over 40 degrees. But you can use it if the equipment's failed or for some reason the compressor isn't satisfying the demand. And we used to say electric resistance, but per recent legal issues, you could have that electric or fossil fuel.
Yeah, I would maybe just go back one point to make is the freeze protection is really important. And it does, in Seattle climate, we get, a week of freeze, and you have to really kind of be thinking about that, because that can I've seen heat pumps crack their heat exchangers in there. So we've got heat trace on all the distribution, but you have to extend it inside of the heat pump and run it around. So that's an important piece manufacturers should be pretty dialed into that. But the freeze is real when the heat pumps are sitting outside. So I guess, yeah, domestic hot water load. This is a typical load. And so the EcoSizer is sort of looking at a design day. It just kind of shows you, but we've metered a bunch of hot water use in buildings. This tends to be more of a market rate type profile. So during the day, people are gone. This is an older curve. It doesn't reflect work from home. It's a little flatter these days in some of our market rate. And yeah, different types of occupancies have different profiles. But we've done senior housing, which is more of a bubble, like throughout the full day. So it's just one bump. They tend to do laundry and stuff kind of in the middle of the day. And we've sized it using these peak curves for senior housing and haven't run into issues on those. I mean, that was just kind of the early days. But we are working on inside of EcoSizer selecting for different occupancies. So that'll be some more capability built in to the EcoSizer. We've kind of talked about this. This is an example of a 30-unit apartment, 60 people, and I think the occupancy is really, is really the important part. And what we like to do in our design engineering work is to really upfront establish what the design occupancy is, because that drives the whole sizing. And I usually like to get the owners to try to commit, like, how many people do you want this system to be sized for? I think that's really important. Again, we talk about sizing. This slide, there's a nominal capacity, and then with all heat pumps, there's a capacity at our design condition. So what's shown in that curve is showing a 24-degree design day for Seattle. We do get down into 19. So it depends on how you want to size, but you can see the difference between 23 and 19 is, it's somewhat significant. But that is the value, the sum of that design point or that capacity becomes what you want to put into the EcoSizer. And so if you've got 2 or 3 heat pumps, which would be good design practice, add up all of those at your design condition, and that's what goes into EcoSizer, not the nominal rating size.
And that would then automatically include the defrost function?
So that capacity that's shown there does not include the defrost. So what that shows is when you've got, steady state conditions, 23-degree air going in, that's how much heat you're going to get out. The reality of what happens is these heat pumps in our climate, about 40 degrees, 45 to 35 is where you're going to see most of the defrost. Once we get below 35, it's really dry out. So we don't see a lot of defrost down at the really cold bins. So it doesn't really play into this peak capacity because down at 12, it's too dry. We don't have enough moisture in the air to, we're not doing a lot of defrost then. We do some, but not a lot. But we do most of it in that bulk 35 to 40 because it's really saturated outside and where the coils are below freezing.
Good.
But what you do have to remember is that, and the reason to have multiple stages on that heat pump plant is that you want some to go into defrost and other ones to run, and then if you get enough stages of it, then that impact is minimized. Refrigerants. So there are some rules on the refrigerant phase out that do get into certain equipment not being part of the phase out, and water heating does trigger some of that. And so at the smaller size, that the phase out, you may not see that happening as aggressively as the HVAC, but the whole industry is phasing over, and all the heat pump manufacturers out there have the next generation of refrigerant. So off we go. But with water heating, maybe next slide to kind of talk. Yeah, so this one talks about the refrigerants, but there's essentially for water heating sort of 3 refrigerants. or actually 4. So there's 134A, that's pretty common. So that cycle doesn't do well with really cold temps. So that's a great candidate for either indoor or in a buffered parking garage. The replacement or the transition refrigerant is after that. That's the sorry, I'm drawing a blank, but the 513, I think that's shown there. But the next generation, replacing the 134A, has pretty similar operating characteristics. Then we've got 410A. 410A is generally good for cold, but not very hot water. So it's sort of the opposite problem. And that's traditionally what's been out there. And then the kind of the newer comer to the market is the CO2 transcritical cycle. It operates a little bit different than the traditional F-gas cycles. But for water heating, CO2 is an excellent refrigerant, and that's already sort of at an end game, with a natural refrigerant. So you don't have any GWP, but that's a great product. But the 134A replacement is called 513A. It just came to me. But there's a bunch of new 513A equipment out there that we're metering right now, and they tend to be, the manufacturers are definitely learning how to work inside of the limitations of that refrigerant cycle. And so there's some pretty cool innovations happening to extend the capacity and useful, temperature range. But yes, the refrigerant stuff is sort of happening, but good to say for us that most of the manufacturers are actively switching to that next phase of refrigerant.
A few years ago, we looked at had a cost estimator do a comparison for us, and found that those CO2 systems you see on the bottom of this chart were actually less expensive per unit than those big things that you've seen pictures of down in the garage with the giant fans and stuff. So not only have you got super low global warming potential, but you've got I think more economical. I don't know how those other guys are going to stay in business personally.
Yeah. So this slide's kind of just highlights air buffer zones. So one area that we've put a lot of heat pumps in are inside below grade parking garages. The ground contact, the deep ground is like 52 degrees, and so that's a great heating source for heat pumps. So when the outside's 25, the garages usually stay above 40. So that's a great application for utilizing some of the F-gas, like the 513A refrigerants. Where you discharge your air when you're in a garage is important. You do have to pay attention to it. If you're buried in the corner, deep in the bottom, I would recommend trying to push the air up a level or two. Especially with, below grade basements come with big buildings usually. But you really want to kind of try to get that air out. The discharge air is 15 degrees cooler. You don't want that to be in a small confined space. And then if you can tap it, if you can locate it near the garage exhaust, that's a great place to put it, because we can tie into the garage exhaust on a temperature and sort of flush the garages out with that exhaust. So it's a great little measure to activate the garage, when the temps drop too low. So I think so this one is just kind of highlighting the Appendix M and kind of showing the impact of sizing with Appendix M. So as you recall or don't, Appendix M is really it's a methodology inside of the UPC, inside of the plumbing code. And it says you can use an alternate. And then the alternate has been developed by IAPMO, and that's called the WDC, Water Diversity Calculator. And that was developed by IAPMO using actual flows. And so those flows tend to be even more conservative than what we're actually seeing in buildings, which is good for a design community. But we've been doing Appendix M. I think a lot of other designers have. and haven't had really any impact. Haven't seen much. This just shows the impact of the sizing. So with Appendix A, it would tell you you have a 260 GPM flow rate, 4-inch main, also 4-inch meter. So when you're designing a new building, trying to get the smallest meter possible will will lead you to the smallest fees. But every year you're charged for that meter cost by SPU. So there's an advantage for the building owners to try to get that meter as small as you can. You can see the difference. It's 4-inch down to 2-inch. That's very typical. That's what we see. And like we saw in those curves, in a 114 unit apartment, the peak's probably half of what that Appendix M number is. Just the reality. And that's a lot of what leads to oversizing of the mixing valves, because I've worked on some projects in California that have Appendix A. They haven't allowed Appendix M, and so they've got 4-inch mains, 4-inch mixing valves on a 50-unit apartment, and it's like, no, we're never going to see anything close to this. So, and of course, the mixing valves don't work because they're outside of their control range. So that's, this is really important. There's a huge advantage, huge cost savings for the plumbers to do Appendix M. It just makes sense all around.
So, and a 2-inch pipe is not half the size of a 4-inch pipe. That's a quarter of the water volume. So an enormous change in your circulating system. Saves money for construction, saves money for insulation, saves money, saves space. You just can't beat it. There's a whole section in the code about water heater equipment efficiency, including this weird equation. But I would say ignore the whole thing, because that's just the federal standard. So your equipment's going to be there anyway. We made a couple changes in the this chart that I really don't like just generally, but it's in the code, that separates out what they call public lavatories from others, to say, yes, you could have 8 feet of piping length from your circulating system to the fixture, not this 1 or 2 or 3. And really, I think this should go away, because it's a subtlety in the plumbing code that they redefined what a public lavatory faucet was to call it only lavatories that are open to the public, that you can just walk in, so there's no security. So maybe a public library or a train station, but hardly anything else actually qualifies in the plumbing code as a public lavatory faucet anyway. We mentioned the Appendix M. There was so much worry among plumbing engineers that this would undersize their piping, that we said, okay, you have to use the Appendix M sizing, but you can go one pipe size larger. There's some concern that people had that by going down to the Appendix M size, you might have a problem just with your flow rate through that whole system. Shawn, has that ever been a problem if you size all the way down to Appendix M, that you run into pressure loss through the system?
I mean, we haven't seen it in a couple of the projects that have been delivered recently. I have heard of supplying the bath fill. So if a project does have a bath fill, that can be really constrained with the 3/8 kind of run out. So those should be 1/2 inch. But I haven't seen any other issue. I mean, all the fixtures are low flow inside of apartments. Feeding them with 3/8 piping has not been an issue, but I think the longer runs, you have to kind of check the pressure drop.
And this is why we're able to use this in the Appendix M in Washington, is that it's only for multifamily. They're working on trying to make it for hotel as well, but still it's just for multifamily and Washington State, and with low flow fixtures. And since Washington State's requirements are also uh, very low flow, then this is no longer a problem. Uh, the the pipe insulation is to have. You can see in this chart that you need, where the blue circle is, you need 2 inches of insulation for circulation loop piping that is not in a partition. So you can like see one of those lateral runs across the basement or something like that. Once you're in a partition, then you just need 1 inch of insulation, because the idea is that you're in a partition that's got conditioned space on both sides, very limited area. It kind of acts as its own insulation. So my diagram here was just showing that on the bottom there, that's the thickness of the insulation you need for your circulation loop. If it's and how thick that starts to get. The top is other runouts or runs that are not part of that circulating system, and those can have less insulation. I wanted to mention, at least briefly, refrigerant piping insulation. That was quite a controversy for a while, but we finally settled on, for the, there's 2 lines, the hot gas line and the liquid line. The hot gas line, if it's outside, needs 1 inch of insulation around it, which is more than was traditionally being supplied. If it's inside the conditioned space, then it just needs 1/2 inch. And on the liquid line, it needs 1/2 inch for mini split systems or anything else that the manufacturer wants it. But otherwise, the liquid line doesn't need insulation for most heat pump types. We have a rule about tank insulation that says that we're presuming 130 degrees, but for every 10 degrees you go up above 130 degrees, we want an extra R2 of insulation. So you could, for some systems, it's advantageous to store water at 140 or 150, something like this, so you can get more heat in a smaller area. Those just need more insulation, and those extra blankets are available commercially. Just a couple clarifications about circulation controls that are, if it's once, I think we talked about this before, if there's a difference between a single riser or single zone system versus a multiple riser system, with our multiple riser, just note again that residential and institutional occupancies don't need to have that full off for the circulating pump system, and we do require that thermostatic balancing valve at the out at the end of each of those risers or each of those zones.
So let's see, this slide is really just trying to show the temperature maintenance losses are really just the losses through that pipe and the delta T across that insulation. On the left, you can kind of see there is a seasonal effect with temperature maintenance loads. And so when you're looking at an existing building, if it has plant or piping in a below grade garage or somewhere outside a heated space, you will see a big variation in that because it's the delta T across that wall, so the water temp across from the ambient. So you do have to be careful if you're looking at an existing building in, say the summertime, the load will be much bigger in the winter. So that's kind of an effect on that. The chart on the right was a sampling of temperature maintenance losses in an apartment. We've coined a term called watts per unit as a loss. So your total piping UA divided by the number of units, or sorry, piping UA times the delta T across there would give you the heat loss rate out, and then that's divided by number of apartments. But if you look at this cumulative distribution plot, you can kind of see that the 70 to 80 watts an apartment is pretty typical. That's what we find for new construction. I've seen loops uninsulated in buildings out to 400. But that kind of shows you that most of your losses are kind of in that below 100 range. Again, this is just a zoom in a little bit, but a four-story electric tanks in the units, about 60 watts an apartment. So that's kind of your baseline. 6+1 project we did measured 64 watts an apartment, 78 up to 86. So there's different reasons why you get those different values. But it comes down to your insulation integrity.
As I mentioned before, we do need a thermostatic mixing valve for each of those branches, and note that in red that if it's a power failure or something, it either goes to cold or keeps its current temperature.
Yep.
And Shawn, we've
Yep.
got like 30 slides to go in about 20 minutes.
Oh, okay. So we talked about mixing valve selection. The minimum rate is just your recirc. The max is your recirc plus your peak hot water flow rate. You want to size your mixing valves in that range to maintain good valve authority. When you oversize them, the valves end up hunting, and you don't get good constant supply temp out.
There are some water heaters that need to have demand response capability built in, so that at some point in the future, our utilities can, make arrangements with building owners to take their systems offline. Water heating is ideal for this, to get us through emergency peak load issues, because we can go for hours just cruising on the stored water. Note that the C406 system has been changed. Typically, one of the old credits is now 6 of the new credits. We made it a little finer grained. See the red circle. You need a certain amount of efficiency credits, and then what we're calling load management credits. So I've circled several things that could be in your water heating system that are good for credits, and I've not seen a lot of use of these. They might be more expensive than other credits available in the system. We also require, I want to just mention commissioning, that you got to, on those mechanical drawings, on those plumbing drawings, if you have to have a note on the drawings that says, yes, the commissioning is going to get done. And at the end of this whole thing, we're now requiring that if there's commissioning issues that were unresolved or tasks that weren't finished, you're going to have to do something to ensure that actually that does get all the way done.
I'll add here, alarms, notifications, and maintenance. This is part of the advanced water heating specification, but super important to have a system that can alarm when there's an issue with anything in the plants, and then also properly trained maintenance that know what to do if there's something that's gone wrong.
And the code is requiring that you at least have alarms for if there's a fault in the equipment, if you've got low leaving temperature out of your tanks, or low hot water delivery temperature. The question I have at the bottom is have you designed who sees these, and not that it just happens into some website that no one will ever find. We do require metering for domestic hot water in every unit in a multifamily dwelling. There are a few exceptions, but this has been a big problem because still some plumbing designers and contractors have not figured this out. And once the building is finished and everything is smoothed over, and the inspector is standing there with a clipboard going, "So where's your meters?" It's a really expensive and unpleasant problem. So make sure that happens.
So I guess this is just another example of a CO2 central system. Not a lot to talk here, but really that these, most of the all the CO2 products out there, which would be GWP1, um, are set up as single pass machines. Some of the systems require a heat exchanger. So some systems you can connect, have the double wall built in, others don't. So you have to be really aware of that. But CO2 systems are some of the highest performing heat pumps that we've seen. And you'll see that in the qualified products list that NEA manages. The CO2 tends to be the top of the list.
And they work fine down to 5 degrees. So Western Washington, it's pretty much handles everything. You don't need any backup heating.
Yep. This slide is showing an example of a recent design, but how to manage the discharge air. So in this case, the air was ducted out of a closed mechanical room, and makeup air was brought in through the floor from the lower level. So the lower level is going to be the warmest level because it's deep ground. And so if you can source your air for those heat pumps from the level below, and then kick it through the heat pumps and then kick it out on the upper level, that's a great way to kind of manage the two thermal resources. Physical space. This is just kind of the same deal, but the space in heat pump water heating systems can be 2 to 4 times more, maybe even more, 5 times more, depending on kind of the systems and size of the building. So we do have to, as we're designing new buildings, we need a lot of space for these systems. So the rooms end up being bigger inside the garages mostly.
So the basic thing about existing buildings is that pretty much you break it, you buy it. So stuff that's been there that was legally installed can stay. This is changing, of course, with the building performance standards that are coming into force. You can repair things that are broken like for like, but if you're replacing something, then that will typically need to meet code. And also, those bottom bullet points, there are 3 things: substantial alterations in Seattle, and then statewide, a change of occupancy from like a storage or utility building to something more polite, or change of space conditioning from unheated to heated, or heated to heated and cooled. Those indicate a big change in the use of the building, and we bring you almost all the way up to new building standards. There's a difference in the Washington State Code. A new system has to comply with what you see inside there, and there's exceptions for several kinds of systems, mostly smaller systems. In Seattle, the exceptions are that if you need a massive electric service upgrade, okay, we'll let you not do that right now. If it's just replacing smallish equipment, that's okay. And we have several exempt building types that because it was just when your water heating goes out, there are certain groups that just have a very difficult time arranging financing and design and all that to do those. You can maintain 50% of your existing gas capacity if you want, and just replace the other 50 with heat pump as the first stage. Or if you have to replace all of your water heating at once, you can give us some assurance that you're going to, within a few years, convert to at least 50% of that to heat pump capacity. So that in any of these cases, you're going to need what we're calling a future decarbonization plan if you're not fully converting to heat pump systems, and that is a fully engineered schematic design and cost estimate. The idea was that schematics are usually 10% of a design project, right? And design is usually 10%-ish of a whole construction. So we're talking 1% of the cost of actually doing the work, but you're going to have to give us a design with all these details on it and a real cost estimate. I mentioned the fossil fuel compliance path. That's the idea is that blue line you see on the top is how much your building would be using if you were fully heat pump. The second line is okay if you want to use gas or electric resistance. Your building's going to use more energy. That additional energy you have to make up for by using C406 credits, and it turns out there's a lot. So there's it's now defined as that primary path. There are a number of exceptions we've built in there to try to soften the blow for some spaces that don't use that much. But here you can see that for an apartment building, an R2 in the red circle in the middle, that is a lot of credits. So I'm finding it hard to believe that people would find that more economical to use the gas water heating and not and have all those additional efficiency credits. But we've seen one project that actually did it. There's an exemption in the formula that allows you not to have to get credits for things that were already allowing electric resistance heat. And it has its own 406 table separately. I'll skip by some of those. It does say that for existing buildings, you don't have to replace with heat pump necessarily if you want to follow that fossil fuel compliance path. We have now, the state Clean Buildings Performance Standard and Seattle's Building Emissions Performance Standards are both starting to kick in, and those are going to require that you get to a reasonable amount of energy efficiency, or in Seattle's case, to zero emissions over the next couple of decades. And so our code says, okay, when you have to replace with heat pump, but we give you options to postpone. It might be that postponing simply means that before the end of the life of that equipment, you'd have to replace it anyway to meet one of those standards. I think this might be getting to my last slide here, but Dave Price at the Seattle King County Public Health has a few bits of advice for having the plumbing permit be easy and breezy. So first, to just check to see whether a plan review is required, or if it's something that can just be dealt with online with inspection. So if you're more than 3 floors, if you're big, if you have special things, then you need plan review. But otherwise, you might not need that. They have a lot of problem with people sending in plan review documents that are not all the way complete. So you can see that link to design guidance thing. They have a nice thing that says all these things that you need to have submit on your plans. You can save yourself a lot of time and delay on your project by complying with that. And finally, somebody has to have a hard copy of the approved drawings, and not something printed out on 8.5 by 11 or something, but big enough to read everything. The approved drawings, so that the inspector can look at those right there. I think with a few minutes to spare, we made it through. Shawn, did you have any final words to the wise before we go on to questions and other things?
No, I think I've kind of covered everything. I think, if there's any questions, I think outside of this, feel free to email me right there, Shawn at Ecotope. Happy to jump on and answer any questions for you.
Thanks.
Yep.
Yep. And we have a handful of questions. Not all. Duane's lying. We have a special guest, John Bringenberg from Wildan, to talk really quick about an upcoming program that Seattle City Light is launching called the Design Assistance Program. John, are you with us?
Yes, Katie. If you'd like
Excellent.
to go now, I'll grab the screen, okay?
Perfect. Yep, go ahead. And then we will then we will get to your questions. So if you had any questions during this time that you didn't write to me in the questions box, do it now.
Okay, yeah, I'm John Bringenberg. Our group is Wildan, and we are the third party administrator, would be the proper term. We call ourselves the implementer for the new commercial construction program for Seattle City Light, and it's called Energy Design Assistance. It's a free engineering level or energy modeling level analysis, and we evaluate what the project is planning to do, and we also make suggestions for things that we can help you analyze at no cost, so that you may be able to achieve some stretch goals in the design. And the program to eligibility includes, of course, projects that are within the city light footprint, commercial, industrial, or multifamily, and are the energy incentives and grants that are achieved by this program recognize measures that go above and beyond code, so that our system and our energy modeling will reveal that and allow us to essentially tweak on that. We like for the projects to be enrolled before the completion of 100% design construction documents. Said a little differently, it works best for your client, for the developer, and for the architects, and for the utility, if we get involved towards the end of schematic design or beginning of detailed design. And there's also if you're a new user of Seattle City Light, there's some conditions there, which that situation doesn't come up very often. You've just listened to a lot of discussion about heat pump water heating, and so just to put a little spin on that, the way this energy modeling protocol works is it sweeps in both central or distributed hot water, whatever makes sense for your project, and then the modeling allows us to holistically determine overall energy savings and improvement over code as a result of the system in the design, not all by itself. And we like to see, honestly, all buildings participate. It is a free whole building energy model protocol, and allows us to collaborate on trying to get more high efficiency options in the design. And then at the end of the process, it provides a significant slug of incentive dollars that goes back to the developer. There's a calculus for it. You can see it here, but we'll of course step you through the calculations to achieve those incentive numbers. And in terms of timing, I mentioned this. I just want to reinforce that the program works best for everyone involved if we do our work together, which feels collaborative during design development or towards the end of schematic design. Once a project is under construction in the red area, it is no longer it's no longer eligible for this program, and there are essentially public policy reasons for that. So there's good reason for that. So it's very important with this program for us to work together early on. When we show you the results of the energy modeling, our group does this in over about 24 states or about 50 utilities, and we've been doing it for some 30 years in some of those places. And over that time, we've learned to be able to simplify and streamline how we take you through this process. When we present the energy modeling results, we present it in 3 baskets. You can think of it as good, better, best. Not because we're trying to have you choose one of 3 things, more so because it greatly simplifies this like live charrette that we go through, and makes it that much more simple for us to be able to help you achieve the most out of the building. I'll just close here with some just anticipating some frequently asked questions about this program is, when does it start? We are we're close to the moment of starting, but we are going to frame that as second quarter 2025. And when we do enroll a project, it takes about 4 to 6 weeks for us to step through the modeling process and have the meetings, but it only takes about 2 hours of meeting time with the team to get the job accomplished. And how much incentive will I get? It's significant, and we describe these again. It's formulas that drive the numbers, but in simplicity, or a simple yardstick, is that we generally see in Washington these incentives come out in I'd say the 20 to 30 cent per square foot up to the 90 to $1 per square foot range and that's a kind of a simple yardstick you could use. And with that, let me hand it back to Katie so we can help you get wrapped up.
All right. Thanks, John. Pretty exciting program coming up. I'm going to put everybody's contact information here back on the screen and get started with Q&A. Thanks to everybody for sticking around. I know we said 11:30 stop. If you need to drop off, as always, we recorded this, so you can come back and see the answers to these questions if you need to do that. All right, so let's start with, Thomas asked, where do you find that Group R and I exemption for the building recirc pumps? That was way back at the beginning when you mentioned that there was an exception, Duane.
I don't have that section number in front of me at this second, but it's right there as an exception to the requirement itself.
Okay. And then Christopher wondered, do you have like a source for the data you'd mentioned or you'd showed a slide that there was measurements done for both Appendix A, Appendix M, did that comparison? Do you have a link to that data, or where you can Google?
Yeah. So 2050 Partners in California was leading that research. We contributed six Seattle buildings to that. There was a data set out of New York, and then a couple in California. I don't have that link handy, but I could go ask the PM to get that, and I'd be happy to maybe just distribute that to you, Katie, and then that could be distributed.
Cool. Yep. I've got everybody's email. I don't mean to be creepy, but I've got all your emails. I can email that out. Okay, and then Shawn, I think you touched on this super briefly, but what implications does having an oversized mixing valve have?
Yeah, we kind of touched on that, but most of the automatic control valves have have kind of a sweet spot where they perform well. What I call that is valve authority. So if your valve has good authority over the flow range and you've sized it right, then you're gonna have really steady mixes. But you'll know right away if your mixing valve's oversized, because it'll hunt a lot. It'll hunt all day, and so what that leads to, or the implication, is that you're going to have variable supply temps. So some during big rushes you might be more in control, but when the system kind of backs off, you're going to lose control. And control means trying to stick within 1 or 2 degrees of your supply output set point. But you just want to make sure you don't dip too far. But yeah, properly sized valve will be able to maintain control. Valve authority is kind of the terminology.
Katie, answer to your first question, C404 .7.1.2, there's an exception at the bottom of that section that exempts R and I occupancies from that control.
Okay, I already deleted the question. I think it was Thomas that asked that. So Thomas, I hope you heard that. Okay, next one. Is the lack of defrost at low temperatures when there's no humidity the reason it was earlier mentioned to use heat tape inside the heat pump?
Um, no, those aren't related. The heat trace is there because you've got water which freezes at 32. And so what can happen is if those systems are not running overnight and it gets cold, that temperature inside the unit will drop. But it's not related to the defrost. The defrost is kind of a separate function. It still does defrost at cold temps. You just don't get as much. Where the action is, in the high 30s. We see a lot because of how moist it is outside.
Yeah, I recognize that from having to scrape my windows when it's just about snowy temperature, but when it's 20 degrees, there's nothing on it.
Yeah.
Yeah. Okay, and Thomas asked, is CO2 single pass only? If so, how do you deal with the cold water being returned to the primary tank when in defrost?
Oh, good question. So what happens is when a system is in defrost, it actually stops pumping. So it's not gonna destroy your precious hot water. It just turns off. So in 1 hour, you run for 10 minutes, you turn off for 5 to melt ice. You go back and run for 10, you turn off for 5. You run for 10. So the net effect is you're not running for 30 to 40% of the hour. That's your direct hit on your capacity that's delivered because you can't deliver anything when it's not running. But that's where multiple stages come in handy because this machine could be still running and the second one could be in defrost, and then you've got a higher probability of runtime when you've got multiple stages.
Okay,
But yeah,
thank you,
great
Thomas,
question.
for that.
Yep.
And question on Ecosizer. Alex says, I know Ecosizer defaults to 50 degrees Fahrenheit entering water temperature. For Seattle area, I typically use a lower EWT, which of course affects sizing. So what would you recommend for EWT here?
Good question. So the city water in Seattle, most of it has surface reservoirs, and those will heat up to 70 degrees by September. The coldest water in Seattle happens in March when all the ice is melting, and so the groundwater is super cold. But the variation is about 10 degrees on 52. So 52 minus 5 plus 5, but then the surface reservoirs take it all the way up to 70 in September. What I would recommend, 50 has been working just fine for us. If you're close on something, then drop it to 45 for local climates. In California, 50 is sort of the low end down there. They're a little bit further south, more sun.
Okay. And Duane, Alex has a question for you too. You briefly mentioned on heat pump water heater the utility data connection. Yeah. I have a few projects that use the C406.3.6 hot water energy storage and understand the energy storage. Was curious if there's a way to know when the utility will provide the peak input and how long it will last.
So this is not a data connection that will be connected up right now. There's nobody asking for it. We're setting these up um, for the future so that it would be City Light actually that would be saying we're in a crisis here. We need to uh, reduce energy use. If in that future there would be agreements that people who are willing to have this functionality um, might get a better rate or something like that. But we're just building in the potential for automatic control from the utility without actually any kind of connection now.
Yep, as a City Light employee can confirm, we cannot have functionality set up yet. And then Chris wants to know, does metering need to be added to individual condo units if the common DHW system is updated?
No, that's that's a new construction thing. If
Okay.
uh, it would depend on the extent of the remodel. We've seen some projects where they're going into an old building where the pipes are all corroded and everything, and they're replacing that whole system. Yep, that would be required. But just replacing the equipment in the basement, no.
Are you going to talk about that in the next alterations webinar?
Are you
Maybe
giving
Chris
us a
should
plug
sign up
here?
for that. Yes, yes.
Yeah, I'm sure that will
Um,
cover.
and then John, there was a question for the Energy Design Assistance Program. You guys do the modeling. Do you take do you take into consideration some people have already worked with a modeler or whatever to do for their designs? So do you take models that have previously been done, or do you do the one that your group does?
No, it's a very, very good question. Thanks. The reason that we use an energy modeling tool is to be responsible for the way we allocate or determine an appropriate incentive for the project. We're spending public funds, so we have to be accountable to that. The energy modeling tool allows us to do that. The fact that there might be, and in fact, there almost always is energy modeling that already is performed by the developers contractors is actually a plus. So that's where it feels collaborative and working together. We're not a substitute for that effort. We're more of a collaboration with it, and we reinforce whatever is there.
Cool. All right. Well, and contact for now, the City Light Energy Advisors if you are interested in getting
Correct.
into that program before it starts even, early adopter. Duane's there, Shawn's there, and our email is there if you have any questions after the fact. And we're going to close it out for today. Thank you all for joining us, and thank you, Duane and Shawn, as always, for knowing everything. And take the survey, everyone. Tell us what you want to learn next. Give us a round of applause, and we'll call it a day. Thank you, everyone.